So 5.2, the flame acceleration in a channel due to the repeated obstacle. So this particular section you are talking about the repeated obstacle, and of course you read through, but I just pointed out by underline, it said in a partly confined area with obstacles. So obstacles means, again, as we talked the other day, it's like equipment, okay? Something is there in the path of the gas-air mixtures, the vice versa here, and the processing equipments, pipings, etc. The flame may accelerate to several hundred meters per second during a gas explosion. So it causes the increased the burning rate. So if the obstacle is there, which means is really equipment is there, what would be a problem? So based on your reading, what would be a problem? Is it equipment is blocking the path? Is it bad? Is it helping? What? Anybody can address on that? Answer, some answer is here, but you could have a more meaningful answer. Is it gonna be okay? What? Burning rate is increasing, gas pressure going to be increasing, which is not desirable. But as another option, if you put the ventilation option, is perforation, platings, some opening in the wall, is it going to help? I think it's going to help, but depend on your design. Sometimes you can open, you can introduce the ventilations as much, but in a limited sense, sometimes maybe not. So it's a depend on, but mostly the ventilation has to be provided to really lower the pressure. So this is what they are talking here in this particular sections here. And I think we talked briefly at the last minute on Wednesday. So this is like a burned gas. This is a tube type here. And this is obstacles here. And the fuel-air mixture will just flow through here. Then turbulence will generate around here. Okay, that's what the reality. Turbulence generation in a channel due to the repeated obstacle. So in the plant design, it seems to be you have to really design even the location of the equipment really well. Okay, and this is again the plate type obstacle, and this is, if you look at this, this is experimentally measured the flame speed and the flow velocity in a 1 meter wedge-shaped explosion vessel with a 5 obstacle. 1 meter wedge-shaped explosion vessel, if you read, you already noticed. We have 3 or 4 experiment this particular chapter introduced. Then you saw the wedge-shaped, 1 meter long wedge-shaped experiment with the perforated plate or a solid plate and vice versa. Then it shows here So it's interesting. Red is a flame speed, and blue is mean flow velocity. This is closed end of the tube or wedge-shaped vessel. Then this is open flow will pass through. This is like an obstacle. And this is distance from closed end is 0 all the way to the 1 meter. And this is depend on, this is open end, this is closed end, and flame speed increase. And also should mention about, didn't say anything, maybe in the reading, in the phrase you might be able to find the type of the fluid, type of the pre-mixed fluid. It may be also affecting parameters. Okay, so this is the mechanism of flame acceleration due to the repeated obstacle constitute a strong positive feedback loop. Here, the combustion of a premixed gas cloud is expanding, then the flow interact with the obstacle, generate the turbulence, then turbulence enhance the combustion rather than laminar flow, then it just goes back into as a positive, the feedback in the system and going into it. And of course, due to the turbulence, pressure will be increased. Then in the second round, the second cycle, then it could go around here and keep doing it. This is some basic mechanism for the flame acceleration due to the repeated obstacles. Some good feedback. So venting combustion product is a very effective way of minimizing the acceleration effect of repeated obstacle. So introducing the venting is obstacle will increase the pressure because of the generation of the turbulence. Then you have to introduce the venting, so it conflicts each other. So you need some sort of the design optimization on that. So that's the situation you will face here. So introducing now the venting and obstacle, which is really equipment rather than obstacle. That's the equipment. And burned gas is moving along. This is a pre-mixed fuel, the air situations. Interesting, isn't it? Okay, and next one is flame speed on the vertical axis, meter per second, and this is the flame position as a meter in the unit. And if you look at this phrase a little bit together, how this is really showing how deflagration decelerate when it propagate from the obstructed into unobstructed region. In this experiment, the flame speed drops from several hundred meters per second to a few tens of meters per second. So that's what it shows. It's confined, initiating the region. Then this is the region of the pipe work obstacles here. Then this is after passing the obstacle, then what's happening in there as a flame speed. So depend on the position, depend on the propagating length, and at the beginning, this is a beginning, then you generate the flame speed quite a bit, then in the unobstructed region, it just die out. I feel that's a common sense, but the magnitude of the flame speed, you can pay attention. This is something like here is 600 meter per second. That's quite a bit. Flame speed. So this is as a result of the experiment. It shows again flame acceleration will enhance the burning, increase the pressure, then venting providing the pressure relief. So it's a conflicting each other. So it affects the design naturally. It's a competing, they use the word. This will say competing effect, confronting each other. Okay. Now it comes the experiments. If you're really going to look at really detail, you have to really look at the actual report or possibly paper as shown here, but this each section for the description of the experiment, it provides a decent description for setup. So this is really descriptions shown from here to here, experiment description, but that's what, as you look at the description, then you can really look through this figure together. This is 10 meter long, and this is a 2.5 meter diameter, 2.5 meter, and there is a jet tube. Then this is the ignition plate. So then there is a orifice because it's opening. So one case diameter of the opening is 2.26 meter. Another one is 2.06 meters. The last one is 1.74 meter. So large opening, medium, and a small opening. So of course the velocity is going to be changing, things like that. And lots of more parameters you have to think. What kind of the fuel, type of the fuel you are going to use it is another matters here. So this looks like experiment was done by the CMR. This inside that tube, total volume is 50 cubic meter explosion tube. The inner diameter is smallest, medium, and large, 2.26 meter through 1.74 meter. And the block gauge is 50%. The block gauge is, in this case, 1.74 diameter hole. And 2.06 is 30% and 16%. So largest diameter opening has, of course, the smallest percent. And you see the configuration. So it's very straightforward tube type, the setup. And this is showing here type of the fuel, propane and the air mixture, and the number of rings, which is really the plate opening. So this is only one ring. This is a 3 ring. And this is for whole 5 ring. This is what 1 through the 5. But I don't know where they put just the 1. The barrier. 3 I could imagine 1 here, 2 here, 3 here. 5 is 1, 2, 3, 4, 5. 1 maybe middle. If anybody can remember, I'm not sure. I don't remember in the report where they put the 1. Anybody remember? So maybe middle. So for a time being, because we are not really investigating the results of this, all the parametric study for this experiment, but in that sense it's okay. 1 ring, 3 ring, 5 ring, and that's a fuel type, and what the consequence would be, that's what we will just use it, okay? And so consequences, I want you to read. If I underlined some place, then we're gonna do that. Otherwise, we'll move on, okay? This is second experiment, wedge-shaped explosion. Wedge-shaped explosion is like this. And few different options, and top plate. And this gray means it's perforated. Then ventilation is possible. And another case here, this is called the distributed venting, when you have perforations at the top plate. And another case is a far and the venting, only this portion has a ventilation option. It's a perforated top plate. This is a solid. This is a solid. And at the inside here, along the length direction, you see the obstacle plate. In this case, this is really cylinder kind. They used also as a square cross section, as a block gauge or obstacle to simulate the equipment. And you have a top plate, but this case is a perforated top plate. Okay, this is 10 meters. No, here is a 10 meters. So that's what the situation is. And as I remember the reading of the report, this is the exit side. I thought this is ignition side. We'll see. Or maybe you could remember when you read also the same thing. So this is a wedge-shaped explosion vessel, wedge-shaped. First one is a tube type. And the purpose of this is again to study the effect of the various types of vent arrangement in combination with the repeated obstacle. But you know, this is what it really bothers sometimes as I really look into detail. What happens if you change the fuel? What's gonna be affecting result as a consequence? sort of the things. What happens if this length is much longer, wider? Can you scale linearly? Maybe not. Do I have to scale non-linearly? What's the function? Is it the cubic function or square functions? How can I project for prototype, for example? A lot of things you must consider. So this report shows really good experimental result for the particular geometry. So that's what sometimes bothers. So here is the case pressure as a gauge pressure and average top confinement. So this is 100% confinement. What does it mean, 100%? 100% confinement, what does it mean? 80% confinement. Youngkin, what does it mean here? Anybody? Confinement. Wedge shape. 100% is solid plate. No ventilation holes and all that. So when you have, it's fully, this is a fully opened, 20% the perforation, 40%, 60%, 80%, 100% is the complete solid. Solid, the no ventilation holes, then pressure increases, right? But interesting thing here is what? When it's about 80% is 80% of the top plates has opening, then from 0 to 80%, the ventilation hole remove the pressure really well. That's what that is. Dr. Kim, I think this is kind of the good result. We can think about it when we design the container, buried container, how much the vent we're going to allow. Up to the 80%, the 80% is confined, which means not much holes. And the pressure relief is really, really good. And we can, that's what this graph is really shows. When you really remove all that ventilation hole, then you will have to be careful. It's high pressure. And this is a far end venting at the edge of the wedge. The end of the wedge. It just, that's the design. And distributed venting is with many holes on the top plate. So this has some meaning for the design. So sometimes its result is quite meaningful. And this is a cubical explosion vessel. So cubical is box shaped like this. So maybe flow, of course, will go through this, maybe that, I don't know. But anyway, this is what the obstacles is. This is a so-called 3x3 obstacle, 3 meter, 3 meter, 3 meter cube. And the obstacle diameter is 0.82 meter. And as you see here, this is what this table is. The diameter of the obstacle, 164 millimeter, 410, 820. And this is a blockage ratio. This is a volume blockage to get 10%, 20%, and 50% blockage. And this is set up. 6 by 6 means is really the cylinder obstacle is 6 per row. And this is a 3 per row. This is what the picture shows here. This is 9, this is 15. I don't see the case for 15 by 15, but if you are really anxious to look at, you have to access a CMR report. You can possibly, if you are anxious to look at the paper or report, you can send the email to CMR. Then CMR people should direct it to some person who handles the whole reports. They may charge, but can get it. Charge is not the issue in Korea. All the days it really matters, but nowadays not the big issue. So that's the case, okay? This is a cubical vessel. So cubical vessel. This is for 3 by 3, 3, 3. This is a peak explosion pressure for stoichiometric perfect balanced propane air in a 27 cubic meter cubical explosion vessel. The 10% blockage, 20% to 50%, and this is for different size of the cylinder. And the blue is 410 millimeter. And what do you call color? Reddish? No. 자주색을 뭐라 그래? Violet? Red. Okay, red. 164 millimeters, and the yellow is 820 millimeters, and peak pressure. Maximum pressure as a dynamic pressure. This is gauge pressure. Again, that means it's a dynamic pressure. If blockage is higher than we expect, and also for that case, which is higher, which is in log scale, 1, 2, 3, about 3.5 bar dynamic pressure. I feel not much, but I feel not much because I'm dealing always for large explosive shock. Maybe that's the reason. But the gas explosion is another bad thing is gas explosion, always remember, combined with the fire. That kills. And gas explosion combined with the fume, that kills. That small village, Busan problem, that give harm to the people, not just the gas explosion. Gas explosion was not the problem, but dispersion of the fume is a big problem. So combining parameters, you have to really think. In that sense, gas explosion has a very serious problem, very serious problem, hazardous problem even if the pressure is not that high like a defense type explosion. This is really what happened at the middle of the ocean platform. People doesn't have any place to go but jump into the water. That's so bad. That's the worst. So it has a good comment as they conduct the experiment. Not only the volume, the blockage ratio is of importance, but also the size and the shape of the obstacles is also important. Blockage ratio, important. Too many equipments could block off the passage, very bad. It just rises, pressure just rises. And also the size and shape is also important. And it's a size here. Here is peak pressure, peak dynamic pressure is a gauge pressure, spherical. I'm not sure why they call it spherical. This is cubical concept. This is wedge-shaped concept. It's cylindrical. And tube is ignition plate is the plane, and also blockage is a plane, so it's a tube. So that's three types. And comparing, relative comparison, I hope. But peak pressure is concerned for this planar situation, generate the highest pressure. Looks like a cubical is generate the lowest the pressure. So I want you to blockage ratio with the channel or sector, different design, then terminal flame speed they are talking about. It is about the same. This is not linear, but two curve is about moving in the same rates. But that's what the difficulties is. This is another experiment, 1 to 5 scale model, and looks like it's more realistic. It's something like the heat exchanger or steam generator or that kind of the layout. And with the lots of tube, God bless you. This is sort of the mini tube, something like, as I recall, heat exchanger, steam generator, in conjunction with a nuclear power plant, you involve something like, as I recall, 800 tube. And it's subjected to cross flow or sometimes a parallel flow. Nowadays, design may be same. I'm talking about, I work at Argonne National Lab in mid-70s in Chicago area. So I really involved on that. And we are talking very small vibration of the tube. Of course, high temperature situation with 3 or 4 feet per second type of the velocity, and lots of problems, the tube thinnings and all that. But for ocean platform, what's the life of the ocean platform? Pengshi, how many years? Once you build the platform, how many years they can use? Anybody has an idea?
20 or 25. 20 or 25 years.
Similar. Nuclear plant is about 30 years. So heat exchangers and steam generator, very important unit, equipment, and about 25, 30 years. So it looks like about the same. So this is a little bit more realistic design they are talking. I want you to read, and it has some more information here, but not sufficient, but get the feel. Same. Shape and arrangement of obstacles, which means it's really equipments. You can read it through. This is the flame speed as a meter per second, blockage ratio, cylinder case. This is an obstacle, cylinder obstacle, square obstacle. Think about the tube type, okay? So you can see 600 meter per second is what you see here. Wedge-shaped vessel for square. This is interesting here. And here, this is what the last, this particular, model. And look at this arrangement here. Arrangement of obstacle. So as you see here, this is among three, this is least obstacle. It has a passage through. Then without looking the relative velocity, you can tell this will have less the overpressure, because the mixture can just go through here. But this is kind of the generate a really high pressure, and this will generate the high pressure. And this is scheme A, scheme B, and scheme C. That's what you see here. C is the third one, as a minimum, has a minimum pressure. It's almost flat, regardless of the blockage. But scheme A and scheme B, this is a scheme B and this is a scheme A. Scheme A, the blockage is a more regular type. This is a little bit more, kind of the irregular type. So irregular type will generate a higher, the overpressure. This is interesting. This case is the absolute minimum type right there, this case. So shape and the arrangement is affecting. There's lots of good result it shows. This is obstruction of vent opening. This is, they are talking about put the blockage in just outside of the vent opening, getting closer, getting a little bit away from the vent opening. That's what they are talking about here. If it's getting very close, it's going to block the vent opening. So that's what they are talking about here. And as you see here, overpressure versus distance of wall. They installed the wall in front of the vent opening. So as is close to the opening, of course, overpressure goes up. And as you set up the wall away from the vent opening, then pressure drops. That's if you, for your particular design, you have to work on for that design, but you have some understanding what happened. So now, after go through this handbook, you should have a general arrangement, understanding of the general and important parameters and all that. So that will really help you, hopefully. And then when you go into the industry or research institute, then things are changing. Then you have to face, in reality, you have to work on the actual prototype models, and you have to relearn the whole thing all over again. That's what. But you have a good basis to attack the problem. So that's what the beauty is. You will struggle. Kyung-seok is struggling for the master's thesis project, because learning is one thing here. Probability of the failure, oh, clear. But combining with the underwater explosion, not the easy task. So struggle. Without that process, without feel the pain, you gain nothing. That's what I keep talking to Kyung-seok. But I don't think he really feel pain yet. But I expect he should feel more pain. Then he will get over. Same thing happened to you. You have to feel the pain. If everything easy, very warm breeze, you know, then you gain nothing. So some sort of the pain in the process, then you will learn a lot. You will appreciate more. That's what's happening. Okay, I think I'm going to stop right here. Then we're going to start 5.9 and Monday. Then at Monday we'll finish all chapter 5. And I want you to go through once again chapter 5. Then we'll continue the chapter 6. Chapter 6 is the detonation. Detonation is a smaller chapter. Then 7, 8, chapter 8, the response calculation. I'm going to spend a little bit more time in response calculation. It's a dynamic analysis. I can tell you a little bit more than you can compute, okay?